see the board.
Better. Yeah. Where's the other one? This one?
No.
What's the definition of B? I write it on the board. It's first U and then Y. Can we start? Well, we are going to use the board extensively. Maybe an idea is that you come close to the front side so that you can see the board better. Of course, if you are able to see the board already, you don't need to move. But maybe you guys have difficulty up there. I don't know. You tell me. You are okay? Okay. But those who are having problems with their sight should, like me, should sit in the front seats. All right, welcome again. Now we are going to continue today. There are no tutorial exercises for today. We are going to continue proving the statements that we didn't prove in the lectures, and some of them were also in the tutorials. Okay? And we are also going to make it a kind of discussion, how to prove. For instance, the first thing, can you show the fundamental lemma? The first thing we want to prove in the lectures, statement 1 was proven the first day, but not statement 2. Okay? Shall we start discussing all together, and in particular two of us, discussing how to prove it? Well, may I start? So, to begin with, one needs to recall the definition of restricted behavior. So we have this system by the way, I often write down A, say B, and mean C. So if there is anything you don't understand or you don't agree, please stop me. It includes Henk as well. I look at this system and define the behavior, B, of this system as all possible input-output trajectories starting from time 0 and going to infinity. And in particular, the restricted behavior say up to some time instant t, is the set. Shall I define also B, maybe?
Yeah, let's do it.
Okay, let's define the B here. These are input state trajectories. Did you define n to contain 0? Yes. And these are, how was it? Up to n, right? So it is something like R m plus p to n. These are sequences. This notation is for sequences with n plus p entries. And there exists an X sequence an X sequence such that, let's give it this set of equations a name, like star, such that star holds. Huh? All input-output trajectories of this system is collected in the behavior. The behavior is the set of all input-output trajectories, sorry. Okay? Now, the restricted behavior is this is something finite dimensional. This is infinite dimensional. Sequence, subspace of a sequence space we are looking at. Such that Uy is an input-output trajectory of the system. So basically, we have the collection of all input-output trajectories, and then we have a time window, and we look at restrictions of trajectories on that given time window, and that gives us the restricted behavior. And this is going to be in r to the power 1. So t plus 1 u's, t plus 1 y's. So it is going to be m plus p times t plus 1. So this is a sequence subspace. This is a subspace of r to the power something. Okay? So we already discussed before how to prove it. I would prove in a different way than Henk proves. You can decide which one is better. My vote is for Henk's proof, by the way. But I would do the following. To begin with, since Uy is just a given trajectory, or finite trajectory, I know that image of that Hankel matrix on the left is in the restricted behavior. Because I take one particular trajectory, I look at on the window 0 capital T minus 1. Therefore, the left-hand side is going to be included in the right-hand side by definition. Which means that the only thing to prove is the reverse inclusion. I should start from an element of the right-hand side, the restricted behavior, and prove that it is in that image. Okay? Of course, this doesn't happen always, only if the input is persistently exciting of order n plus L, and also AB is controllable. But I already made those assumptions. Okay? So the way I would approach is the following. First of all, I make an observation. I can write this restricted behavior, or the one over there with 0L minus 1, in terms of certain matrices. And that are given also in the next slide. You see this omega L and theta L, right? So now, first I claim that this restriction is nothing but image of 0 omega L identity theta L. Okay? Why is that so, you may ask? Huh? It is because if I look at a trajectory of this system, let's look at the trajectory of this system and let's write, for instance, to have an understanding, let's write U0, U1, U2, Y0, Y1, Y2. Huh? Let's write this down. Well, I write, okay. I can take x0 here, u0, u1, u2 here. This is an n vector. Okay. So this has n columns. Now, u0, u1, u2 is equal to u0, u1, u2, right? The first part is okay. Let's look at y0. y0 is equal to c of x0 plus d of u0. So it is c of x0 plus d of u0. And then comes zeros here. Right? What is y1? y1 is equal to, y1, let's write y1 here. y1 is equal to c x of 1 plus d u of 1. But this guy is equal to a x of 0 plus b u of 0. Therefore, y1 is equal to c times a times x0 plus c times b times u0, d u1 and 0. I continue doing this, and I'm going to have ca to the power 2 here, cab here, cb here, and d here. Right? Upper one. Okay. And so if I multiply, so this is, maybe I can write even identity, 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 and zeros here to make it clear. 0, 0, 0. Let's look at this one. 0 times x0, identity times u0, it is u0. And this is going to be u1, this is going to be u2. And that is what I have on the left-hand side. And obviously, I can do this. I can continue writing this down. And then you see the structure of omega L and theta L, right? Agree? So we agree that we have this equality.
Well, Kanat, why does the equality hold now?
Why does the equality hold? Yeah, well, this is the difference between me and Henk. I was not trained as a mathematician, although I'm a professor of mathematics. He's trained as a mathematician, so he always asks these terrible questions. That's a good point, because what I have convinced you here is that which direction I have shown. So if I start from an element of this, I prove that it is in the image of this. Yeah, this argument. But the same argument can be reversed. Because if I take something in the image of it, of this matrix, it is going to be this matrix times some vector, and it is going to be in the restricted behavior. Of course, there is a catch because I need to continue to forever, so that I can obtain something in the behavior. But that has to be done. Whenever you need to show that one set is equal to the other set, unless there is a super special structure of the problem, what you need to do is to take one element from the set on the left, show that it has to be an element of the set on the right, and then do the other way around. It is also the same to prove two real numbers are the same, for instance. First, you could prove that I want to show A is equal to B. A, B are given with some properties. The generic way of showing it, first you take A and show that A is greater than or equal to B, and then you show B is greater than or equal to A, or reversing order. And then you prove, therefore, they are the same. Dimension of? Which one? This one? On the left? Yeah. Yeah. Yes. It's okay. Yeah. 3 here, 3 here, yes.
So the t is 2.
T is 2, because from 0 to t. So once we have this equality, then can we go back to the and so now I know something about the right-hand side. Left-hand side is about given data. Okay? Therefore, I already automatically know that image of Henkel L U and Henkel L Y is in this restriction. And why is that so? Because if you look at the Henkel matrix here, the first column starts with U0 up to U of t minus 1, Y0 up to Yt minus 1. That has to belong to this restriction anyway. The second column, though, starts from U1 and runs up to Ut, Y1 up to Yt. But we are looking at a time invariant system. If you have a trajectory and shift it by 1, it is still going to be a trajectory. Therefore, the second column needs to belong to this restricted behavior. And then you can do again and again. All the columns need to belong to this restriction. Okay? Well, here is another kind of trick in proving two subspaces being equal. So I have this inclusion already to prove, I need to prove that everything here, if I take an arbitrary element here, vector here, it needs to belong to this one, right? But this can be done in a couple of different ways. And from this point, up to this point, we agree. But from this point onwards, we diverge. Henk takes the direct approach, takes an arbitrary element from, as far as I understand, right, from the restricted behavior, and he's going to show you how you can prove that it is in the image of the Hankel matrix. And I'm going to take a different approach. It is informative because sometimes one doesn't work and the other works. In this case, both work, but it's better. What is better than one method? Two methods. I'm going to look at the dimension. Since I know the left, the subspace on the left is included in the subspace on the right, to prove equality, I need, it's enough to show that they have the same dimension. If they have the same dimension, they must be the same subspace. Okay? And in some situations, this is the only way to prove the subspaces are equal, actually. I can give you an example, but not in data-driven settings, so I skip it. So that's my approach. So I'm going to look at the dimension of this guy and the dimension of this guy and show that they are the same. Dimension of the restricted behavior I can already see from this expression. Because it is equal to the rank of this matrix. What is the rank of this matrix? Because of this identity, it is going to be rank of the matrix omega L plus the size of this identity matrix. So, maybe I can use, I can continue here. So I put a question mark, oops. I put a question mark. Is dimension of image Hankel L U Hankel Y is equal the dimension of the restricted behavior on 0L minus 1. That's the question. Okay? Now I do the following. First I write the dimension of B. So it is equal to the rank of omega L plus size of this I, it is L times M. Now, it is enough to sorry. It is enough to show that this other dimension is the same, right? But how can I find out the rank of this matrix? The dimension of the image is the rank of this matrix. How can I find the rank of this matrix? Well, since these guys are generated by the system, there must be a state trajectory such that the Hankel, I think it is also on the other slide. Sorry, this is L, right? You see, I made a mistake and nobody warned me. Oh, sorry, this is T. Sorry. sorry. Okay. This is equal to, again, 0 omega L, identity theta L times x Hankel L U, and this is x0 t minus L minus 1. Hankel L. Hankel 1, okay, that's a better notation, yeah. Hankel 1 of x 0 t minus L. Okay? So how can I conclude that rank of this guy is equal to rank of this matrix actually? Huh? Why is that so? It is because we have already proven in part 1 that that matrix, which is this one, has full row rank. Therefore, these two matrices must have the same rank. Because maybe I can also write that down. Shall I make a window here? When it comes to making conclusions about rank, the most important tool is rank nullity theorem. It's a very cute result. It is about an arbitrary matrix, let's say M, with M rows and columns. And it says that the dimension of image M plus the dimension of kernel M add up to N. And by looking at the transpose of these matrices, if necessary, from the fact that the very last matrix has full row rank, I can conclude that these two matrices must have full row rank, and therefore this matrix has rank. I'm going to write it in this way, is equal, and then I will write rank here, which means that it is rank is equal to this exact term. And then we are done. Okay? Now Henk is going to show a proof which is going to take 2 lines after all, at least showing the equality of the restricted behaviors.
Well, as an alternative proof, we already know by Kanat's explanation that the image of the input-output Hankel matrix is included in the restricted behavior. So the only thing that we have to show is the reverse inclusion, namely that the restricted behavior is included in the image of the input-output Hankel matrix. So let's see how we can show that. Would it be very rude to erase your argument, or oh, we can do this.
Oh, there's a piece of art.
Well, in that case, I prefer to erase yours.
I think it is better. That's the flag of Pakistan, isn't it? I like to think
So we need to show that the restricted behavior of the system is included in the image of the input-output Hankel matrix. So what you could do is take an arbitrary length L trajectory in this restricted behavior and show it's also in the image of this Hankel matrix. So I'm going to do that. So let's say that we have this restricted trajectory. So I denote it by bars. So U bar, Y bar, just to distinguish it from the data. Right, so this is a restricted trajectory. And then using Kanat's formula over here, I know that there exists some initial state of the system. Let's denote it by x bar 0, such that this relation holds. Right, so there exists some x bar 0 in Rn, such that this restricted input-output trajectory is equal to, now we use the shorthand notation on the slide, right? So this is 0 identity omega L theta L times x0 bar U bar 0 L minus 1. Like that. Okay, very good. Now I will again use the fact that we've already shown item 1 of the fundamental lemma in the lecture. So I know, by the fundamental lemma, maybe we can go back actually once more to the slides. Yeah, we know that item 1 holds. So this state input Hankel matrix of the data has full row rank. It has rank n plus ml, equal to the number of rows of this matrix. Now, what does it mean? For a matrix to have full row rank, the image of that matrix is the whole space, right? It's Rn plus ml. Which means, actually, that from item 1, we can now say that there exists some vector g. It's in Rt minus L plus 1, such that if I multiply this state input Hankel matrix with this vector g, like this, I get exactly this x bar 0, U bar 0, L minus 1. Right, the reason is this vector x bar 0, U bar 0, L minus 1 is some vector in Rn plus Ml. Since the image of this matrix is the whole space, obviously I can find some vector G such that when I multiply with this state input Hankel matrix, I get precisely that barred vector. Right? Okay, good. Well, now what I do is the following. So I look at the input-output Hankel matrix of the data. And I multiply with this G. Okay, let's try to use now the formula in the exercise. Right, so I replace this input-output Hankel matrix using the formula on the slide. So what is this? Well, this is 0 identity to, well, omega L theta L times the state input Hankel matrix. So that's the first part, and then I still need to multiply with G. Okay, nice. But we had an expression for this multiplication of this matrix with G, and that was written over here. So I replace that by x bar 0, u bar 0, L minus 1. So, copy the first matrix, 0 identity, omega L, theta L, and then I have x0 bar, u bar, 0, L minus 1. Like that. Okay. Yeah, but now we're there. Because you see that indeed this matrix, 0 identity, lambda L, or is it a lambda? It's omega L, theta L times this x bar, u bar, is precisely this input-output trajectory that we started with. Right? It's u bar, y bar. Which shows indeed that this arbitrary trajectory, u bar, y bar, we took from the restricted behavior, is in the image of the input-output Hankel matrix, right? Because it's the input-output Hankel matrix times some vector G. And that proves the result then. Well, it was not exactly 2 lines. It was a bit longer. Any questions about this? No? Shall we then continue with another exercise?
The proof of the deadbeat controller.
Yeah, let's do that.
Yeah.
Would you like to?
Yeah.
Good? Yeah.
Can we also put the slides?
Sure. Let's go to the stabilization part. That's the most relevant here.
Yeah. Can you show the definition first? Why don't you open the... it's not here.
It's not here. It is.
Yeah. Yeah. So in day 2, we proved we proved conditions, we proved the necessary and sufficient conditions for informativity for stabilization by state feedback. And there was also a question during the lecture whether we can assign the poles, like in pole placement, arbitrarily, like one can do in a model-based approach. And we have also deadbeat controller story. Okay? Now I'm going to do something that unifies all these three. Stabilization, pole placement, or the deadbeat control. Okay? Something more general. What I want to do is first to define a new informativity concept. Okay? Where's the eraser? Oh. Yeah, it's here. So I want to do something which is going to have some special cases, namely stabilization, deadbeat control, or pole placement, all in one shot. Okay? So what I want to do is the following. I want to change the definition of informativity for stabilization by something else. First, I start by defining stability domain. Okay? This is basically a subset of complex numbers which have the following property. Okay? I say CG, G for good. Okay? So, this is not a, it is not non-empty. It contains at least one real number. These can be made more general and so on, but let's keep it as simple as possible. And it has this property that if Z belongs to this set, then the conjugate of Z also belongs to that set. So it's symmetric with respect to the real axis. Okay? For the purposes we have, actually this would be enough for in general, but for the purposes we have, I'm going to also assume that CG is bounded. Okay? So it is bounded. Now, if I want to look at stabilization, I want the eigenvalues of the closed loop system to be in the unit disk, so I can choose the unit disk as CG. Right? Which satisfies all these properties. If I want to look at the deadbeat control, Then I define CG as the singleton zero set, the origin. It satisfies all these properties. If you want pole placement, you specify some poles. Then you take that CG. Well, maybe in that case, of course, the second is not going to be satisfied, so I can add one real number. The reason I want this intersection to be non-zero is because depending on the parity of n, if you have an n by n matrix, if n is odd, it has always a real eigenvalue. Because complex eigenvalues come in pairs, conjugate pairs. So I don't want to distinguish odd and even, and therefore you can throw one real number. It's all right. Okay? So now the definition is that Ux are informative, U minus X are informative for, how shall I call it, pole placement, for pole placement by state feedback with respect to CG if the rest is the same, but instead of stable, I'm going to write the spectrum of A plus BK is contained in CG for all, if there exists a K, such that for all AB in CG.
In sigma.
I told you, I write A, I say B, and I mean C very often.
But would you call this pole placement? Because you have this subset, right? With pole placement, you assign the eigenvalues exactly.
Very good point. How shall I call it then?
Maybe we can ask them.
Because pole placement typically refers exact placement. Yeah, of course, depending on what, classically it means that. Placement doesn't mean that you place things in just one position. It can be also in a set, in a region. But indeed, pole placement has that meaning already, so it's better to call it in a different way. What shall we say?
What about CG stabilization?
That's also a very good idea. G. And then I don't need also with respect to CG, That's very good. For CG stabilization, for CG stabilization, by state feedback, if there exists a K, such that, But you know, I once got into trouble with that, because, of course, it was not a typical pole placement, but it is not stabilization either. Because stabilization refers to something else. I got into trouble with one reviewer. This is standard, by the way, in linear system theory, at least in certain circles. Instead of studying stability, you define this more general stability notion with respect to a stability domain, and you call it CG stability, and everything works as in the same way all eigenvalues must be in CG instead of having negative real part being in the unit disk. But of course, it is not stabilization. But in the motivation for CG stabilization comes from the following fact. Of course, we want to stabilize the systems, but sometimes we require more. We want to assign poles further away from the imaginary axis in continuous time or close to zero in discrete time. So it's on top of stabilization. That's why CG stabilization makes sense. But do you see where I am heading to? It's a unifying approach to feedback stabilization, deadbeat control, or pole placement. If I can solve this problem, I can provide necessary and sufficient conditions, then I am done. Well, if we go back to the slides of the second day, and then to the proof, this was the statement, right? Now I claim that the only thing I need to change is B. Instead of x plus x minus dagger stable, I need to write that the eigenvalues of x plus x minus dagger is in CG. I don't want to write it down because everything is the same apart from the fact that in B there's a slight modification. So I'm going to write that the same theorem and only x plus, only change is stabilization for CG stabilization I need to talk about. This is one change. And the second change is instead of stable, I have this inclusion. Let's see if it works. Well, suppose A and B hold. This is the if part. I take an arbitrary data consistent system. I write the defining relationship. It gives me, but if I multiply by the right inverse mentioned in B, this is what I get. So I can choose K to be this, and also instead of stable, I know that the eigenvalues of this matrix must lie in CG. Therefore, I'm done. So if part is exactly the same, but instead of stable, I need to use CG stable, and that's it. Yes? Yeah.
In the neighborhood of some eigen, other than the exact point.
No, you can also take it doesn't need to be discrete. For ordinary stability, I take it as the open unit disk. For deadbeat control, I take as the origin. For eigenvalue placement, I can take this n eigenvalues. But you can even take disconnected regions. Any region you can take within complex domain. Well, it needs to satisfy this because we know that we are dealing with real matrices and complex eigenvalues come in pairs. So if I is not satisfied, things get a bit complicated. B is, sorry, 2 is to avoid, to distinguish the n odd and even cases in the proofs. Huh? And the 3, I assumed I'm going to use now in the only if part. So this is a general, more general theorem than stabilization. So only if part. So in the only if part, I know there is a k such that a plus bk has this property. So eigenvalues are in CG. And this is true for any AB in sigma. Huh? I continue. I take an A0, B0 with this property. Huh? Then I see that this new pair, A plus alpha A0, B plus alpha B0, satisfies the defining property of data consistent systems. Therefore, this new pair is also a data consistent system. And this is regardless of the value of alpha. And now, I, by the way, corrected the slides, but this is an older version. A transpose needs to be on top of the parentheses. Now I multiply A0, B0 by A0 plus B0K all the way transpose. It satisfies the property A0, B0 satisfies. This allows me to obtain yet another data consistent system, and it is given by this pair. I'm not going to read it out. And again, for any alpha, this pair is a data consistent system, which means that for that k, if I look at nu A plus nu BK, it has eigenvalues in CG. So let's write this down. So this M alpha matrix is nothing but nu A plus nu B times K. And it has eigenvalues in CG for any alpha. Okay? Now, here I use the fact, the property that CG is bounded. If I look at now, limit alpha tends to infinity, the spectral radius of M alpha divided by alpha, since eigenvalues of M alpha is in a bounded region, this limit goes to 0. Okay? If I did not assume that property on CG, I could not make this step. So the limit is 0. Let's look at what that limit is. Well, if I divide by alpha, I'm going to have A plus BK divided by alpha, but it's a constant matrix for when A, B are fixed. In the limit, it goes to 0. And the rest does not depend on alpha, so I'm going to get the spectral radius of this A0 plus B0K transpose times itself. And it's spectral, it's a symmetric positive semi-definite matrix. Its spectral radius is 0 if and only if it is 0. And then the rest is the same, because I don't need to invoke any arguments related to CG anymore. First, I see that A0 plus B0K must be 0, and this holds for any A0, B0 with that property. Therefore, I can conclude that identity K needs to be equal to x minus u minus times f for some f. And that f needs to be a right inverse of x minus because identity is equal to x minus f. Then I showed first A holds, and then there is this f, right inverse. The only thing I need to show that the eigenvalues when I use f are in the region CG. But if I use f, then this x plus f is nothing but a plus bk. And the eigenvalues of a plus bk is in CG. So this is a bit more general than ordinary stabilization, deadbeat, or even pole placement. Well, what if I drop the assumption CG is bounded? There are things one can say still, but in most of the cases, especially in discrete time, we are going to be interested in bounded regions of complex plane anyway. In continuous time, it would be a little bit different then, because even ordinary stability does not have this property. So one needs to do something else. But in discrete time, the most interesting even stability domain has this boundedness property. Any questions? Let's have a tea break here then. This is new, huh? And on the fly, huh? You noticed it because I couldn't remember CG stabilization even. I had difficulty to name it.
So, welcome back everyone. I want to continue saying a few more words about lecture 3. So remember in that lecture we were talking about input state systems affected by some process noise. And the particular noise model that we were considering is given on the slide here. So we were assuming this quadratic matrix inequality on the matrix W minus. We also saw some special cases of that noise model. For example, energy bounds on the noise. And at a certain point I also explained to you that in the case that you have sample bounds on the noise, namely in the case 4 here on the slide, every noise sample is bounded in norm by some epsilon. So instead of having this energy bound on the noise, we assume now pointwise at every point in time, the norm of Wt is less than or equal to epsilon. In that case, I explained to you that that also implies an energy bound on the noise. And namely, I could take this particular matrix phi 1, 1, and then the W minus matrix indeed satisfies this quadratic inequality. But the reverse statement does not hold. So if for that choice of phi 1, 1, my noise satisfies this quadratic inequality, it's not necessarily true that all the noise samples satisfy this pointwise bound, that the norm of Wt at every time is less than or equal to epsilon. So, by transforming this sample bound on the noise into an energy bound, we lose something. We introduce some conservatism. Now, the big question is then whether I could somehow improve the conditions for informativity for quadratic stabilization if we have these sample bounds on the noise rather than energy bounds on the noise. Right? So of course I could go through the conservative way. I start with this sample bound on the noise. I write down this energy bound on the noise. Indeed, that introduces some conservatism. I can write down an LMI. That's going to be sufficient in this case for informativity for quadratic stabilization. But in general, it's not necessary for this particular sample-bound noise model. So the question is, can I do better somehow if I have these sample bounds on the noise? Is that clear, the question? Okay. So, what I'm going to do now is the following. Indeed, I'm going to study the same system as we had in lecture 3, here given in the equation 1. But this time, instead of the energy bounds, I'm going to assume these sample bounds on the noise. So the norm of Wt is less than or equal to epsilon for all time t. And for some given epsilon positive real number. Well, if I do that, I can again write down a set of explaining systems, or a set of systems consistent with the data. Sometimes, this was actually a big debate between Kanat and Harry and me. Should we use sets of explaining systems as a terminology or sets of data consistent systems? And we still haven't decided yet. So that's why sometimes I'm saying sets of explaining systems, so systems that are explaining the data, and sometimes I say data consistent systems. I hope that that doesn't create any confusion, but these are synonyms. So the set of data consistent systems, sigma, is given by all AB pairs, for which the norm of xt plus 1 minus axt minus but is less than or equal to epsilon for all time t between 0 and t minus 1, given here. Okay. Again, in this context, I define informativity for quadratic stabilization. So I say that my data u minus x over here are informative for quadratic stabilization if there exist matrices P, positive definite, and K, such that this Lyapunov inequality holds for all A, B, and sigma. So again, this is the same definition for informativity for quadratic stabilization that we've seen in the lecture. The only difference now is, of course, that we consider this different set of systems consistent with the data. Because our assumption on the noise changed. Instead of the energy bound, we have this sample bound on the noise. That's the point. Now, what is my goal? My goal is to prove this statement that you see here in B. Now, in particular, I want to show that my data, u minus x, are now informative for quadratic stabilization if there exist matrices, P and L, and scalars beta, and alpha 0 up to alpha t minus 1, such that this matrix inequality over here holds. So what is different from the lecture and this other noise model? Well, you see here that instead of having a single scalar alpha, we now introduce t of these scalars, alpha. Alpha 0, alpha 1, up to alpha t minus 1. All non-negative. Such that this matrix inequality holds. Right. So let's try to see why this is indeed true. Okay. Well, maybe I can start because I also want to change slides. I want to show you something. Let me copy just this matrix inequality. Oops. So I have this matrix, P minus beta I, 0, 0, 0, 0, 0. And then in the last column block, I have 0, P, L, P, L transpose, P, 0. So this is the first matrix that we have. And then we have minus this sum from t is 0 up to capital T minus 1 of the alpha t's. In this case, we have multiple alphas times this matrix on the left. So that is identity xt plus 1, 0 minus xt, 0 minus ut, 0, 0. Times the matrix in the middle. So what is that? Well, that's epsilon squared. Identity 0, 0 minus identity. Well, in fact, in this case, the identity is just 1 by 1, so I can write minus 1. And then I also have the transpose of this matrix on the left. So that's identity xt plus 1, 0 minus xt, 0 minus ut, 0, 0. And this is positive semi-definite. So this is the inequality that we're working. Well, I want to remind you of one thing from the lectures. So we had this Schur complement lemma. The result over here. And I now want to apply that to our problem over here. So what do I do? Well, I view S as this big matrix over here. The S22 I view as just the matrix P. So I make this partition. This block, 3 by 3 block matrix over here, denotes the S11. And the P here denotes the S22. That's a partition that I'm making. Okay. Well, as always, we're assuming that the matrix P is positive definite. So now I can apply, let's see, statement 3. I know that S22 is positive definite, and then I know that this whole matrix S is positive semi-definite if and only if the Schur complement with respect to this P is positive semi-definite. So let's write that down. So this is if and only if the Schur complement with respect to the 2-2 block is positive semi-definite. So that is the matrix P minus beta I 0, 0, zeros. Let's see, minus this S12, so that is 0 P L times P inverse 0 P L transpose. And then I still need to copy minus the sum of alpha t from t is 0 to t minus 1. The 0 blocks drop, so I get identity xt plus 1, 0 minus xt, 0 minus ut. This middle matrix, epsilon squared, identity 0, 0, minus 1, and a transpose of the matrix on the left. So identity xt plus 1, 0 minus xt, 0 minus ut, transpose. And this whole thing needs to be positive semi-definite. Right? Okay. Well, to make the notation a little bit milder, let me give this a name. So I call this matrix over here NT. So in contrast to the situation where we had energy bounds on the noise, now we also have multiple matrices NT, depending on a particular sample of the input, the state, and the shift of the state. Okay. Well, let me continue now. So if I now introduce this change of variables, like I had before, so I use the fact that K is equal to L P inverse, then I can substitute that in this inequality over here. And what do I get? Well, I get the matrix P minus beta I, 0, 0, 0, 0, P inverse P, with a minus sign becomes minus P. I get minus Kp minus P K transpose. Wait, am I doing this right? Well, let's see. I get over here. Well, let's try to work this out. I did make a mistake with the transpose, I guess. Yeah. I should use Kp over here and minus P K transpose over here. Okay, it's okay over there. So this is the matrix on the left, and then I still have minus the sum from t is 0 up to t minus 1, alpha t, and this I called nt. And this should all be positive semi-definite. Right? Okay. Good. Now I take a b in our set of consistent systems. So AB is in sigma. Right? And what I'm going to do is I'm going to multiply this inequality from left by identity A transpose B transpose, and from right by the transpose of that matrix. So let's see what's going to happen. Well, so I do this, identity A transpose B transpose, and the transpose of this matrix. I multiply now with the matrix P minus beta I, 0, 0, 0, 0, minus P, minus P K transpose, minus K P, minus K P K transpose, minus the sum of alpha t and t times identity A transpose B transpose. And this is still positive semi-definite because if you multiply a positive semi-definite matrix from right by a matrix, from left by its transpose, you preserve positive semi-definiteness. Okay. Very good. Well, let's try to work this out. So I don't think I need this anymore. So let's look at the first term. Well, the identity times the P minus beta I times the identity term over here is going to bring in P minus beta I. Right? Well, and the term over here, I always like to write that in the following form. So I'm just considering the 2 by 2 block matrix over here now, right? You can equivalently write that as minus I over K, P I over K transpose. And that makes it a bit easier to see then if you multiply with AB and A transpose B transpose, that you get exactly minus A plus BK, P A plus BK transpose. Do you see that? I can, because if I take the transpose of this matrix, I get A next to B. A next to B multiplied with I over K gives me A plus BK. I have the P in the middle over here, and then the transpose of this A plus BK on the right. Okay. Very good. So, this gives me something larger or equal to the sum of t is 0, t minus 1, alpha t, identity A transpose B transpose, and t, identity A transpose B transpose. Okay. Well, let me just remind you of the fact that this matrix NT, that was the 1 to 3 by 1 to 3 submatrix of the matrix that you see over here, right? So everything excluding the last column of zeros and the last row of zeros. So what does that mean? Well, I want to understand a little bit what happens when I multiply that NT with this identity A transpose B transpose from left and right. So, okay, what do I get? So this is identity A transpose B transpose. Times this I next to xt plus 1, 0 minus xt, 0 minus ut. The epsilon matrix in the middle, and then we just have the transpose of this whole thing. Okay, let's look at this product. So what is that? Well, that's just identity next to A next to B times this matrix over here. So what I get there is identity next to xt plus 1 minus A xt minus B ut. But that's just equal to wt. Right? Then I still have this epsilon squared identity matrix over here, multiplied with the transpose of the guy on the left. Like this. Okay. Good. Yeah, so what do I obtain? If I work this out, I get something like epsilon squared identity minus wt, wt transpose. Okay, what can we say about that? Well, hopefully we can say that that is greater or equal to 0, but I still need to prove that. So how to show that? Well, I start from the assumption that we make on the noise. So the norm of wt is less than or equal to epsilon. And that's equivalent to saying that wt transpose times wt is less than or equal to epsilon squared. Right? Well, what does that imply? Well, I just take everything to one side. So epsilon squared minus wt transpose wt is greater or equal to 0. Now I use a shoe complement argument. By the way, my motto is that every day that you don't use a Schur complement argument is a failed day, of course. Huh? At least once you use Schur complement every day. So I'm doing it here. So I'm going to write this matrix, epsilon squared, WT transpose, identity, WT. And I claim that this is now positive semi-definite. Why is that? Well, again, let's have a look at this Schur complement lemma. I add it here. So, S22 is positive semi-definite, positive definite, because it's the identity matrix. So this matrix is positive semi-definite by item 3, if and only if Schur complement is positive semi-definite. But what is Schur complement? Well, it's epsilon squared minus WT transpose, identity inverse, so identity, times WT, which is indeed greater or equal to 0. So the conclusion is that indeed this matrix over here is positive semi-definite. Okay. Now I do it one final time. So I take one more Schur complement, not with respect to the matrix I, but with respect to epsilon squared. Because this whole matrix is positive semi-definite, now, using item 4, I see that also the Schur complement with respect to the 1-1 block here is positive semi-definite. So identity minus WT, 1 over epsilon squared, WT transpose is positive semi-definite. Okay. That implies if I multiply by epsilon squared, that also epsilon squared identity minus WT transpose is positive semi-definite. So let's go back. The conclusion is that indeed the thing that I calculated here is positive semi-definite. Well, what was that thing? That was this NT matrix multiplied from left with this identity AB matrix and from right the transpose. So we concluded now that this matrix must be positive semi-definite. Right? Okay, let's backtrack then. That means that this matrix over here is positive semi-definite. All the alphas are greater or equal to 0, which means that the sum that you see over here is positive semi-definite. Nice. But then we're almost done. Because what can we conclude then? On the left-hand side, well, P minus A plus BK P A plus BK transpose is greater or equal to beta I, which is positive definite because beta is positive. So indeed the Lyapunov inequality holds for AB, hence the data are informative for quadratic stabilization. So ta-da, we proved then this theorem. I can call it a theorem now. If there are matrices P and L with P positive definite, and these scalars beta and alpha 0 up to alpha t minus 1, satisfying the inequality over here, the data are informative for quadratic stabilization. But a nice thing is that you can show, and actually one example of that is here in item C of the exercise sheet. But one can show that there are data sets for which this inequality over here with the T alphas has a solution, but the inequality without the alphas over here does not have a solution. So indeed, in the case of sample-bounded noise, you can do better by solving this linear matrix inequality with the T multipliers alpha. Yeah, so that's nice. In the sample-bounded case, you can improve. Any questions about this? Yeah. Yeah. Yeah, S is always assumed to be square. Yes. Yes. So. No, so in the case that these blocks are not square, then you cannot use this Schur complement idea. No. So S, you always assume to be square. S11 and S22 are square matrices, yeah. But S12 does not need to be square, right? So S11 and S22 can be of different sizes. Any other questions? Mm-hmm. Yeah, so that's an assumption we make on the noise. So this is a prior knowledge. You assume that your noise satisfies this bound, and then we can prove informativity for quadratic stabilization. Yeah. If you don't have assumptions on the noise, you can never solve this problem. So you can never have guarantees that your controller is going to work for the true system. So you need an assumption on the noise. Yeah, in practice, what you could maybe think of, if you do not have a good idea about that, is to be, let's say, maximally robust against your noise. So what you could do is solve this linear matrix inequality while maximizing over epsilon. So try to be maximally robust against the noise. But of course, if you don't know that your noise satisfies that bound with epsilon, you can never guarantee that your controller is going to work for the true system. So for theoretical guarantees, you need to bound on W. Any final other questions? No? Okay, let's stop then here, and yeah, we'll continue again tomorrow.